Hello everyone. Uh, Thing is, I'm a little tired today. I didn't get enough sleep, and yeah, this is all I'm going to do today. Just do this one video, and then I'm going to just lay down. Right. What is this video about? So this particular graph, this is the graph of this integral. We just make this larger. So it's integration from 0 to pi upon 2 of sine ut upon sine t to the power of 4 dt, right? Yeah. And here u, that's the variable, and t is just a dummy variable for this integration. So how does this thing change with u, right? That's the aim. And notice it's power 4 over here, and last time I did power 2. And the thing is, for all even powers, you do get a solution that, I mean, you can manually find out. The problem is that for any general power 2m, at least I right now don't have a general solution. That is, I don't have, um, I don't know, some kind of simple polynomial function or something using just m and n. No, I don't have anything like that, because it involves binomial coefficients and everything, and basically a really big series. And yeah, and that's why I don't have a general solution, but I do have solutions for specific cases which are small enough for me to actually manually calculate them, right? So this thing f of u equal to a. So why is this a here, and why is this 2 upon pi? So 2 upon pi because this whole integral is going to be pi upon 2 times some number which I'll call c naught. C naught is, I mean, you will see why we are calling that c naught later on. Just 2 upon pi and then this integral, but then we are trying to scale this up by a. So that's what this function is. And then I also have this other function. Where did that go? Right. This is the same scaling factor a, and that times of this thing. So u times 2u square plus 1 upon 3. So my claim is that this function in u, right? So 2 upon pi, integration, all that stuff, that's in fact identical to this function mod of u times 2u square plus 1 upon 3, right? And yeah, I even graphed out the thing. So I graphed these out, tf of t and tg of t from -10 to 10 and negative 10 to 10 once again. And then I have nf of n, which is a variable point, so it varies with n. And what's k? K is just a to make a more manageable. And yeah, let's start to this. So n, as we change this, right, this point moves, and so there are two labels over here, a black label and a green label. The black label is for this point and the green label is for this point. Both of these points lie on these curves respectively, so this guy lies on this green curve, right? So yeah, and this guy and g of n, that lies on this curve, right? So as you can see, both curves look very much the same. You might even think that they are actually the same, except that they are not. So if I zoom in, right, just keep on zooming in, you will see they are not exactly the same. It's just that this purple curve is a very good approximation of this thing. That is, it actually works on integer values of n, but otherwise it's just an approximation. It won't work otherwise, right? I mean, it won't give you the exact solution, but it will actually give you the approximate value of, yeah, okay. So that's cool, right? And I even plotted out some of these points on this thing. So at n equal to 1, you have g of 1 as the value of that integral. Yeah, okay, understandable, right? So as n changes, so as n changes, you can see what's happening. Yeah, I mean, it looks like it's on both the curves simultaneously. It's not, but at the integer point, so look, this point, it exactly matches up. So these two y coordinates are the same. If it's not an integer point, then these y coordinates are different. So yeah, there's very little difference, but these are different, right, in the end. And at integer points, as you can see, it matches up. So just for a brief moment, okay, this is so hard to align. Maybe like moving it like this is better. Oh yeah, okay, cool. So right, this changes like this. Yeah, okay, whatever. So n equal to 0, right? That's this point and so on. So you can also manually check if this actually works out. I mean, of course, it's hard to do like sine 3x upon sine x to the power of 4, integrating that thing. It's a hard thing to do, right? Uh, but yeah, from here you can see that it can be done, and in fact, we even have a general formula for this thing. Whenever u changes, how does this thing change? So right, let's get to it. Let's see how do we get this thing. So our aim is just to figure out the integration from 0 to pi upon 2 of sine of, let's just use nx. I mean, here I'm using ux for the function. Technically, it's supposed to be nx, right? Sine of nx upon sine x, and all of that to the power of m. Okay, so m is for general. Okay, let's just use 4. That's gonna work. dx. So, my strategy in solving these questions is, the thing is, trigonometric functions are representable using complex exponentials, and in this particular case we can write it as a complex exponential polynomial. So what I'm saying is sine of nx, that's going to be equal to z power n plus z power negative z power negative n upon 2i, and then that thing upon sine x is just z minus z power negative 1 upon 2i, where z is just e power ix, right? Okay, then this thing of course can be written as a geometric series, right? So this is going to have, let's think, you already got n terms starting from 0 to n minus 1, but then you also going back, so actually 2n minus 1 terms, right? Okay, so you got those many terms. So the thing is, it's just it's, let's just not say polynomial because it involves non positive values as well, right? So negative integer values. Maybe just create a new word right away. Pseudo polynomial. Yeah, pseudo polynomial. That's all. That's what we'll call it. So it's a pseudo polynomial, right? So this is like z power n minus 1 so on till z power negative n plus 1, right? And then you want to make this to the power of 4, right? Of course. So the thing is, it's basically some kind of pseudo polynomial. If it was a polynomial, you would have believed what's going to happen. Even if it's a pseudo polynomial, it still is okay. You can do this by multinomial coefficient and everything. When you expand this, it's going to be equal to z power 4n minus 4 plus some terms. We don't really care what those are. And then finally, the last power would be minus 4n plus 4. And in between that, somewhere you have a 1, and then everything here and everything here. So the integration of these guys, so think about it, z power I don't know, call it as m or something. Yeah, so z power m when m is not equal to 0, right? uh, that is just cosine of m times x plus I sine of m times of x. And because this thing is so symmetric, right, so it's symmetric in and negative, and you can just pair up everything and then only get the real part. So basically it's going to be 2 cosine of m times of x times some kind of coefficient. The thing is, it's not m of x, actually. Yeah, it's supposed to be m of x, right? Yeah, sure. So now the thing to notice is that, like, when you will integrate this out, so cosine of mx, right, you will integrate this from 0 to pi upon 2. If m is an even integer, then this whole thing will just be 0, right? Because the deal. Sine of mx upon m going from 0 to pi upon 2, if it's negative, sorry, if m is an even integer, it's going to be, yeah, right, it will cancel out. That's understandable, right? Yeah, because like 0 to, of course it must cancel out. What am I saying? Sure. So like, let's think about it. Sine, right? So sine at n pi values is 0, and that's why it's gonna cancel out. The more immediate reason for this thing is because in the first two quadrants, so it basically like m times of x is going from 0 to 2n pi, right? Yeah, okay, yeah, where like n would be m upon 2. You get the idea, right? So in the first two quadrants, if you go from 0 to pi, the cosine values, those add up to 0 because the center of mass of this whole thing is somewhere over here. Understandable, right? So it has x coordinate being 0. It's good. Okay, so we just need to make sure that all of these have even powers, and then you're good to go, right? Yeah. Uh, right. So how do we make sure that these only have even powers? That is, there should not be any term with odd powers in there. So there's four of these guys, and look, so first guy starts off at n minus 1, and then this is decreasing by 2, right? So the next guy would be z power n minus 3 and so on, right? Yeah, exactly. So what you can do is just, take z power negative n plus 1 out of this. So this would be z power negative 4n plus 4, and then you just got z power 2n minus 2, and yeah, some stuff like that. It's about 4. Last year got 1. So this is already an even power, and then when you will expand this, you can see that it's going to be only even powers because the starting term is an even power and it's decreasing by 2 all the time. So in the end, you just get an even power, right? The important thing is that 4, it must be like an even number because this must be an even power. So now what? So we have established that other than 1, everything else is something like z power m, or I should just say z power 2m, where m is not equal to 0 and is an integer. So then its integral, right? So the real part of that integral will be 0, but then the imaginary part is 0 in any case. So the thing is, we just want to integrate this term, right? Oh, it should not be 1, it should be like c0. Yeah, I mean, the expansion doesn't necessarily have to have 1 as the constant, right? It could be anything. And then, okay, these coefficients are 1, but then other coefficients might not be 1 or anything. It would be anything, right? So this integration, basically it's going to be c0 pi upon 2. That's what we want to find. What is c0? And that's why I did this thing, 2 upon pi and this integration. So that's going to give us c0 values. And of course, times a, which scales this up, right? So the real question is, how do you figure out what c0 is? So c0 is the coefficient of x power 0 in this guy's expansion, which is also the coefficient of of z power 4n minus 4 in this guy's expansion, right? Or okay, let's not do that, okay, so guys, z power 0 in this guy's expansion, right? Yeah, but the thing is, doesn't matter if you talk about z or some other variable. The expansion is pretty much the same thing, right? Yeah, except that instead of z, you just write something else, say x. So c0 is also the coefficient of x power 0 in the expansion of x power n minus 1 and the same whole series, x power negative n plus 1 to the power of 4, right? And now because it's in some other variable, what we can do is we can apply some restraints on x. So we'll say that x only goes from 0 to 1, right? So then you can write it like this. We could write this over here as well, except that it was not very defined at 0 because, yeah, right? So at x equal to 0, this, oh, and by the way, this x and this x, both of these things are very different, right? This x is just, okay, maybe I should not use x. I don't care about this. Call this in theta or something. Yeah, and then you just say z equal to e power I theta. Understandable? So whenever theta would be 0, this thing would go to 0. This thing would also go to 0, right? So you might say, oh, it's not defined. How do we do the integral? Well, no, it is defined like this series. So you can still do it, and then you can define it as the limit as theta tends to 0 of this thing. So no big deal, right? It's still doable. So now the real question is, how do you get the quotient of x power 0 in this guy's expansion? So we can write this thing as x power n minus x power negative n upon x minus x power negative 1, just like always, to the power of 4, which can be written as, so it's going to be x power n minus x power negative n to the power of 4. And then you got, oh, you know what, just take that 1 upon x out, right? So you will just get like what? You will get x power negative 4 in the denominator. So basically x power 4 in the numerator, right? and now it's going to be just x square minus 1, but it's in the even power, so it doesn't matter. 1 minus x square is also good enough. That is the power of negative 4 because it was in the denominator, right? Okay, that's nice. And we just want the quotient of x power 0 in this guy's expansion, which pretty much just means we want the quotient of x power. Hey, this was correct or not? I mean, it was in the denominator, right? And it came out. Of course, it's correct. So we just want the quotient of x power negative 4 in this guy's expansion, right? Notice that the highest power in this expansion would be 4n, and the lowest power would be negative n. Sorry, it's gonna be negative 4n, right? And then these are all just yeah, all the powers over here, they're going to be positive or 0, right? So in that case, the lowest power would really just be negative 4 and the yeah, okay, think about it. So highest power from here is x power n, that's x power 4n. Yeah, and then if you multiply any other thing than 1 with that guy, so like 4n plus 1, I don't know. Okay, maybe you can also say that n could be 0, right? That's one thing that can happen. You might as well just say n could be 0 or negative numbers or whatever, so that you can actually extend this to non-natural number values as well. So in that case, okay, but the thing is, right now just considering n to be a non-zero equation. Okay, so whenever you multiply, okay, first of all, we should write down the expansion of this. It's going to be 1 plus 4x square, and then you got negative 4 minus 5 upon 2 is supposed to be 10, right? So 10 and then negative, right? Yeah, that's going to be negative x square square. Okay, so positive. So positive 10x power 4 and so on, whatever. That times this thing. So the thing is, we just want x power negative 4, of course, and yeah, right. Okay, it's gonna give us x power negative 4n as well. So this guy's expansion would just be like x power 4n plus 4x power. So go down by 2n, by the way, right? So this would just be 2n plus x power x power 0, and then plus x power negative 2n 4. Sorry, and this will be 6 over here. Sorry, I'm just really sleepy right now. Okay, and then you got plus 4. Oh, by the way, it's negative, right? So it should be negative, positive, negative. Okay, and then it's supposed to be n. And then plus, oops, okay, x power negative 4. Yeah, that should do it. So what I'm saying is, you want x power negative 4 from like this whole thing times this whole thing. So all the other powers that aren't negative, so these powers, well, they are automatically disqualified, because this times any power with which is not negative, right? Yeah, that's never going to give us x power negative 4. That is assuming that n is actually non-negative, and then we'll just extend this by looking at the graph. Yeah, no big deal. Right, so n is non-negative, assume that, then you can just disqualify these guys. And also this, I think, because yeah, we're gonna get that. So it's just these two guys basically, right? So now let's start. X power negative 4n, and to get x power negative 4, you have to have x power 4n minus 4 basically. So when does that happen in here? So that's gonna be negative 4c. Oh, already just got one over there. That doesn't matter in the end. So negative 4c. What was the thing once again? 4n minus 4, right? Yeah. And then negative x squared to the power of, oh, it's already just squared. Okay, then it should be 2n minus 2. That would be better. So it's gonna have 2n minus 2, and then x, so negative x squared to the power of 2n minus 2, right? Yeah, I guess that works out. Okay, that's going to be the coefficient contribution from this guy, and then from here as well you get something like negative 4 is already there, and then you got x power negative 2n. So really just need like 2n minus 4, so half of that is going to be n minus 2. So it's going to be negative 4c n minus 2, negative x squared to the power of n minus 2, right? So this thing is the coefficient that we're looking for, of course. Okay, yeah, awesome. Now the thing is, we know that negative a, c, b, where a and b are positive, we can write that thing as a plus b minus 1 cb, but that times of negative 1 power b, right? Yeah, I mean, it's just like negative a, negative a, negative 1, so on till negative a, and then the last term, so in the progression would just be b minus 1, so negative of that thing. So you got these b terms on the numerator and then upon b factorial. And then you take negative out of every term, so you get this thing, no big deal, right? So for this guy, what is negative 1 power b? It's going to be negative 1 power 2 minus 2. But, oh, and by the way, we just want 1 over there. We don't want this x squared or anything. Yeah, right? We just want the coefficient, not the term. So negative 1 power 2 minus 2 is already there. So 2 times of that, square of that, sorry. That's going to be 1, right? So that just means we are only left with this part. So a plus b minus 1, this thing plus 4, that's going to be 2n plus 2. That minus 1 is just going to be 2n, 2n plus 1. So 2n plus 1 c, and then you got b, just 2n minus 2. That's this guy. And similarly, you can do the same thing over here. It's like minus 4, and I think it's supposed to be n plus 1, right? And then you got cn minus 2. That's the thing. And then, of course, you can write this as 2n plus 1 c3 minus 4n plus 1 c3. That's going to be like 2n plus 1, 2n, and then 2n minus 1 upon 3 times of 2, and then minus 4 times of n plus 1 times n minus 1 upon 3 times of 2. Well, this can cancel, just get 2 and this cancels. Similarly, over here, this cancels. You can take n out, and then it's going to actually take n upon 3 out. So just 2n plus 1 times 2n minus 1 is like 4n squared minus 1. And then minus of this, oh yeah, it's going to be minus n squared plus 1, right? Yeah. So, wait, is that like, no, okay, you got this 2 over there. That's not supposed to be just that. It's, so minus 2 times of this thing. So minus 2n squared and then plus 2. It's going to be n upon 3, then got 2n squared plus 1, which is exactly what we got. So, yeah, I mean, the same thing can be extended to not this function. I'm saying the same method that can be extended to like to the power of 6. Whenever this is to the power of 6, right? So it would be like this thing. Then as well, you can just do this whole method and then you will get the answer, right? So awesome. And there are a lot of these kind of functions that can be represented using let's just say polynomial series, then some power of these, or basically just polynomial functions of the exponential, right? The complex exponential. And then if somehow your integration bounds are such that like either the real part or imaginary part cancels up, most likely the real part should cancel out from most of the terms, right? Only then can you get a huge simplification. For example, over here you got huge simplification because all these things, they became 0. I mean, the real part became 0, but in the imaginary part was going to be 0 from the integration anyway, so we don't have to worry about that, right? So yeah, that's it. Okay, fine. So I'll see you in the next video. Bye.